Welcome back, folks. Our goal today is to do more examples of direct proof. So to start with, I'm going to do several examples of direct proof using our definitions about sets. So let's prove that if A, B, and C are sets, and C happens to be the union of A and B, then C minus A is a subset of B. Before I even start, I want to emphasize what it is we're really proving when we're proving that one set is a subset of the other. Remember here that if X and Y are sets, the definition of X is a subset of Y is if little x is an element of big X, then little x is an element of big Y. In particular, showing a set is a subset of another set is itself an if-then statement. So it is itself going to be proven using direct proof. So here's what I need to do. I need to start this exercise by supposing all of the if stuff, which includes this if stuff, but it also includes the if that is part of the definition of subset. So in this case, namely, it is going to be X is an element of C minus A. Now, to remind ourselves where we're going here, you will often see people write this. You will often see people write WTS colon. And so what this means is want to show. And so the thing I want to show is that X is in B. Why is that what I want to show? That's what I want to show because that finishes the if-then statement that was my definition of C minus A as a subset of B, which is the thing I was doing up here. I'll note, logically, this want to show is not really doing anything. You don't need to include it, but when you're writing these things by hand and you don't know where it's going, it's helpful as a guidepost. So that's where I'm trying to go. X is an element of B. But before I can get to X is an element of B, I need to do a little bit more work. Namely, I need to write down this X is an element of C minus A. So since X is an element of C minus A, I can use my definition of C minus A. Namely, C minus A is the set of all the things that are in C that aren't in A. So, namely, since X is in C minus A, X is in C, and X is not in A. Here I've just again written out the definition of something. Namely, in this case, I've written out the definition of set minus. Now, since C and A union B are equal, that tells me that X is in fact an element of A union B. But A union B is the set of elements that are in A or B. So by definition, X is in A or X is in B. So now I want to draw your attention to these two pieces. X is not in A, X is an element of A, or X is an element of B. And I want to make the observation that since I'm being told this part of the OR is false, and yet the whole OR is true, that means this part must be true. So since X is in A or X is in B, but X is not in A, we have X is in B. That's what we wanted to show, so we're done. I'll say a little bit more about this OR piece in a second. But before I say more about the OR piece, I want to just go over the overall structure of this proof. So I was asked here to prove that one set is a subset of the other. I realized, that literally means this if-then statement. So in this case, if X is an element of C minus A, then X is an element of B. So I went ahead and I structured my proof so that I supposed this if at the start but also this if, which was x is in C minus A. And then I worked through that using the definitions of all of my favorite set things. So I got to use union and set minus and all of these things. I worked through that until I got to that x was in B, but then that finished my proof. Whenever you're showing something as a subset of something, that's always how this is going to work. I wanted to make one more note about this thing we did with the ors, and that is I wanted to make a note about a useful observation about or. So or, remember, is this. And I want to compare P or Q with not P implies Q. So not P implies Q. What is that if P is true and Q is true? Well, as soon as P is true, not P is false, so the implication's automatically true. So this goes true, true. When P is false, not P is true. And so then this is true implies true. That is true. But then when P is false, not P is true. And so then this becomes true implies false, which is false. In particular, P or Q is logically equivalent to not P implies Q. And also to not Q implies P. For exactly the same reason, you can write down the truth table and see that it also works this way. Now, I'm not saying you had to think of it this way, but I think this is useful, and you'll see why later a number of times, to note that an or statement is really itself an implication. And so in this case, what did I do? I realized that the or statement x is in A or x is in B was really equivalent to x is not in A implies x is in B. That is all this is saying here, is that because this or this, not this implies this. Okay, and so that's what we really did, is we said, okay, we have x not in A implies x is in B, and also we have x not in A, therefore we have x is in B. That is all of the magic that happened. And you don't have to think of it in these terms in order to make sense of our proof, but I think that's a useful framework in which to think of these things. Everything we do in this chapter with direct proofs, you should sort of be able to translate back to definitions and to propositional logic. That is, to things that you can sort of boil down to truth tables. Really, it's all a combination of those two things. So here's another example. And here I would again encourage you, pause the video, try and do this example yourself before we write it down. So I'm going to start by supposing A and B are sets. But what else do I have to suppose? If you didn't pause to write this down, at least answer this question. What else do I have to suppose before I can start this question? And the answer is, I also have to suppose that little x is an element of A minus B. I don't have to call it little x, but I have to suppose something is an element of A minus B. Again, the reason for this is because being a subset is an implication. And so what being a subset is the implication if x is an element of A minus B, then x is an element of A union B minus A intersect B. So suppose A and B are sets, x is an element of A minus B. Then I need to write out the definition of x is in A minus B. So then x is in A, and x is not in B. Okay, and now I need to work towards this. Now, notably, x being in A tells me something about A union B. Namely, it tells me that x is in A union B. A union B is the set of things that are in A or B. It's in A. It's definitely in A or B. Very similarly, the fact that x is not in B tells me that X is not in A intersect B. Again, the intersection is the set of things that are in both A and B, but it's already not in B. That's already enough to tell me it's not in both A and B. Thus, if we put together these two pieces, then we get what we want. Thus, putting those two pieces together, since X is in A union B and X is not in A intersect B, that is exactly the definition of saying X is in A union B minus A intersect B. And if you remember that we were trying to show an if-then statement, where the if was that X was in here, and the then was that X was in here, we got to the then, and we're done. Please note, by the way, that when you're dealing with set operations, you really need parentheses to emphasize order. So this would not really make sense without parentheses unless you want to say that you have agreed upon an order of operations for set operations, which I definitely haven't. So we really need parentheses here to say I'm computing those first and then subtracting them so that I don't take A union B minus A intersect B or some weird nonsense like that. Let's now prove that if A and B are sets, then A minus B is A intersect B. A few notes first. First, this might be surprising, because you might mentally think, okay, well, if I just distribute this, I'll get A minus minus B, and so you would think, okay, the A is going to go away, and I'm just going to get B. And so you might expect that if you think this works like algebra, it's just going to work out to be B, which it definitely doesn't. Bourbaki has this thing, it's like an arrow like that just means danger, something is going to go wrong if you're not careful. Okay, and so the danger here is algebra doesn't work on set operations. E.g., if I take A minus B, that's not A minus A plus B equals B. No. Okay, it's not that. One particular thing, by the way, you might notice is there is no plus defined for sets. There's only a minus. So as soon as you see this plus, you should already be pretty worried that something has gone awry. But you're not at all to be blamed if you're inclined to do this kind of thing, but I'm just warning you, it is not going to lead good places if you do. This is just a matter of the notation that happens to have been chosen for these operations. And the next note is, here I've actually asked you to prove something different than we did in the previous two exercises. Namely, I've asked you to prove that two sets are equal, rather than that one set is a subset of the other. There's a method to do this, and the way to do it is to just do the thing we've been doing before twice. Namely, if I want to prove that sets X and Y are equal, I need to do two proofs. Namely, I need to prove that X is a subset of Y, and that Y is a subset of X. This is called, by the way, mutual inclusion, meaning inclusion in both directions. And that's what we're trying to show. Anytime someone asks you to show that two sets are equal, they probably want you to show mutual inclusion. Anytime you're using a specific proof method that has a name, other than direct proof, you should call that out in your first or second sentence. So here I'm supposing A and B are sets, and then I'm indicating to the person who's reading this, the method we're using is mutual inclusion. And that tells the reader what they're to expect. Namely, they're to expect me to show that A minus B is a subset of A intersect B, and that A intersect B is a subset of A minus B. You absolutely have to do this when you're writing proofs. You have to tell the person who's reading it what they're looking at. It is customary, although this is not obligatory, to highlight the sections by which direction you're proving. So I'll write this to show that I'm going to show that this side is a subset of this side. And so if I'm showing the left is a subset of the right, I need to start by supposing I have an element of the left. So I'll suppose that I have an element x of a minus b. Now I need to write out what that means. So thus, x is in A, but x is not in A minus B. Again, note this word but is just a fancy way to say and that just reads a little nicer in English. But this but logically is nothing but an and. Now, what does x is not in A minus B mean? In other words, I'm being asked, what's the negation of x is in A minus B? So here it's worth taking an aside. We won't write this in our proof, but let's do a little bit of scratch work. What is the negation of x is in A minus B? Well, that's the same thing as the negation of x is in A and x is not in B. But what's that? That's x is not in A or x is in B. This is one of our straightforward negations. X is an element of A, the negation is x is not an element of A, the negation of and becomes or, and the negation of x is not an element of B becomes x is an element of B. So x is not an element of A minus B means x is not in A or x is in B. So let's copy that from here. So since x is not an element of A minus B, by what we did above, that shows me x is not an element of A or x is an element of B. But I can make a note. Namely, and this should look familiar, x is an element of A, but x is not an element of A or x is an element of B. Well, x is not an element of A, because it is an element of A. So x is an element of B. Effectively, as you write a proof, what you're doing is you're taking a bag of stuff that you know that's true, and you're putting it together, which gives you new things in your bag. So we had this piece in our bag and this piece in our bag, but we put those two together, and that gave us this new piece, which we can now use in our bag. But now that piece, I want to actually combine with this piece and say that since x is in A and x is in B, well, what does that mean? That means x is in A intersect B. Again, when you're saying something that's combining two pieces that you've said before, you should always restate those pieces and say how you're combining them. You do not want your proof to read like a scavenger hunt, where each line you're saying, well, I can see this thing from the stuff before, and I'll leave it to the person who's reading it to find the two pieces you have to put together to find that. You definitely don't want to do that. You want to say, okay, I've already shown this, so together they give me this. Likewise, just like we did here, he said, okay, I'm combining those two pieces, that gives me that. Just be careful you're clearly elucidating what's happening. Now, I have finished the forward inclusion. Namely, I've shown if I start with an element of A minus B, it always ends up in A intersect B. But remember, I'm not done, because the thing I'm trying to prove is that these two sets are equal. I now have to work the other direction. I now have to show that if x is in A intersect B, then x is in A minus B. So that is to say, I have to show this direction. Now note, what's really happening here is I've just showed one direction of an implication, and I'm really being asked here to show the converse of that implication is also true. That is, here I am proving the other direction of the same implication. So to do that, let's write out the same thing. So what does A intersect B mean? That means x is in A and x is in B. Now I'm trying to build back to a minus b. So let's start with a minus b. Well, x is in a and x is in b. So putting those two facts together, I can at least know that x is not in a minus b. Indeed, literally, being in a minus b means that you're in a and you're not in b, but this is in fact in b, so x is not in a minus b. Indeed, really, this follows literally only from the fact that x is in b. You don't even need the bit about x being in a. But now I want to put those two pieces together. So x is in a, and I want to put that together with x is not in a minus b. So thus, x is in a minus b. But, in fact, that's all I was going for. I'm now done. Again, what does it mean to show something's in a minus b? It means to show it's in a, which we already have, and it's not in a minus b, which we already have, so we're done. Okay, we've shown both directions of the inclusion, and so we have shown these two sets are really equal. Now, I want to note we can make some intuitive sense out of this thing we proved with Venn diagrams. Please note, a Venn diagram is never a proof. So when I ask you to prove things, you can write down Venn diagrams to help yourself reason through them and think about it, but it's never going to prove the thing. You're going to have to write down something like what we just wrote down to do that. Let's put in blue dots, where is A intersect B? Well, A intersect B is this part. And note, it's all of this. I'm just shading it in blue dots to say it. A is over here. Where is A minus B? Well, A minus B would be this crescent. Okay, so A minus B is this piece. And so when you take all of A, which remember is this whole thing, but you subtract off A minus B, that lops off this moon-shaped piece over here, you are, in fact, you can see left with this A intersect B here in the middle. So hopefully that makes this make both intuitive sense and also lets you understand how to prove it. So that should give you some sense of how to work with sets in proofs. Next up, I'm going to do some examples of problems where I give you a definition and then ask you to prove things about the definition. So I'll give you a new definition in the proof, and then you'll have to use that definition to prove something. So, first off here, we have our definition. A real number x is called 2phi if there's a k in the positive integers such that 2 to the k times x is an integer. Notice we started here with a real number, and so it is not at all clear that this thing is going to be an integer. Sometimes it is, if we're lucky. So here's what I want. I want to prove that if I start with two 2phi real numbers, and I add them, I get something that is still 2phi. Now, whether I ask you to or not, whenever you encounter one of these definitions, I encourage you to first write down some examples and non-examples. So, what are some examples of 2phi numbers? Well, 4 is 2phi, so is 10. So, in fact, is any integer. Pause and convince yourself that all of those things are definitely 2phi. On the other hand, there are lots of things that are not 2phi. So, for example, pi is not 2phi. Square root of 5 is not 2phi. 1/3 is not 2phi. If I multiply any of these things by a power of 2, it's never going to make it an integer. A power of 2 divided by 3 is never going to be an integer. Square root of 5 times a power of 2 is never going to be an integer. Likewise, pi. On the other hand, 17/4, this is 2phi because I can multiply it by 2 squared, and that will give me 17, which is an integer. Similarly, 3/8, all of these kinds of things where I've got a power of 2 in the denominator and an integer in the numerator, all of those are going to fall under this definition. But any irrational number like pi, or any fraction with an odd number in the denominator, those will all fail this definition. We haven't proved anything, but we've given ourselves at least a little intuition with which to work to try and make sense of this statement, just to get some sense of what things meet the definition and what things don't. So now let's prove this thing. Okay, so we're going to suppose that x and y are 2phi. And then I immediately need to unwind that out of the definition. What does that mean? That means that there exist k and l in z plus such that 2 to the k times x and 2 to the l times y, these things are both integers. And now what is it I want to show? I want to show that x plus y is 2phi. That is, I want to show that there exists some integer m such that 2 to the m times x plus y is an integer. Now, ultimately, the fact that this thing I want to show is a there exists statement is telling me I'm going to have to find an m. I'm going to have to write down an m and say, this m works. And that m is probably going to depend on k and l that I put up here. And you can play with a bunch of different things, and there are a bunch of different ways that you can do this. But I think ultimately the cleanest way to do this is like this. I'm going to choose m to be the sum of k and l. And then I'm going to look at 2 to the m times x plus y and say what that is. Well, that is 2 to the k plus l times x plus 2 to the k plus l times y, which is, by properties of exponents, 2 to the k times 2 to the l times x plus 2 to the k times 2 to the l times y. Now, 2 to the k times x and 2 to the l times y are the things I know about. So I'm going to rewrite this again as 2 to the l times 2 to the k times x plus 2 to the k times 2 to the l times y. Now, it's worth pointing out, we know this thing and this thing are integers. So let's give them names. So then what is this? So then 2 to the m times x plus y is what? It's 2 to the l times a plus 2 to the k times b. But what do I want? I want to know that this thing is an integer. But I have that now because this is a product of two integers added to a product of two integers. But if you multiply two integers, and then multiply two other integers, and then add it together, you definitely get an integer. So since a and b are both integers, 2 to the l times a plus 2 to the k times b, this is an integer. But then that exactly means that x plus y is 2phi. But that's what I wanted to show, so I'm done. Again, we had to work with the definition we were given, and we actually had to use that definition in this case, both as part of the hypothesis of the implication and also as part of the conclusion. So we had to translate both ways. We had to translate out of the definition to start, do some work, and then translate back into the definition at the end. So let's do another example, and this one will be a lot like a lot of the homework through the semester. We'll go ahead and come up with this definition. We're going to call a subset of the integers lonely if, for every element of it, that number plus 1 is not in it. So let's start with just writing down a set, and let's ask whether this set happens to be lonely or not. So what is this set? This is the set of all numbers that can be written as 3 times an integer plus 5 times an integer. And it might take a bit, but not too long, before you realize that this set includes 6 and 5. So because 5 is in here, that's x is 0 and y is 1. And 6 is in here, that's x is 2 and y is 0. Since 5 and 5 plus 1 are both in here, it's not true that for every element of this set, we have x plus 1 is not in S, and thus this set is not lonely. Now what we did there really was to intuit the negation of lonely. But it is often worth your time in these examples to explicitly write out the negation of the word you're talking about. So how do I negate this? Okay, and so for every x in S becomes there exists such that, and then x plus 1 is not in S becomes x plus 1 is in S. So verbatim, the negation of lonely is if there exists an element such that that element plus 1 is also in the set. And so what did I show you for this set? I showed you that 5 is in the set and 6 is in the set, so this set is not lonely. Now, very often throughout the homework packet and throughout life in math, you're going to be given statements and you're going to be asked not just to prove them, but to prove or disprove them. In the real world, almost everything you encounter mathematically is a prove or disprove statement. Because, of course, if you already knew whether the thing was true or false, you would not need to prove it. And so lots of these things, when I ask you to prove or disprove them, will be true, and lots of them will be false. So which is this one? This one is actually true. And so what that means is I have to include a proof. And so let's write out the proof. Okay, so we will suppose T is a lonely set, and S is a subset of T. What is it I want to show? I want to show that S is lonely, which is to say, I want to show that for every x in S, we have x plus 1 not in S. But, and this is a really important point, this for every statement we can rewrite as an equivalent if-then statement. And the reason why that's nice is that we know how to prove if-then statements. Namely, we need to also suppose this piece and then get to this piece. So let's do this. So I've supposed now all of the regular if stuff, but then I boiled out the definition and figured out that this secretly was also if stuff, so I've also supposed that. And already this is pretty messy, so if you were typing this up for your homework, you would go back and hit some backspaces and start with suppose T is a lonely set, S is a subset of T, and X is an element of S. But, well, I'm writing this in pen, so I can't backspace. What is it I want to show again? I want to show that x plus 1 is not an element of S. But I don't know much about S, but I know a lot about T. But I do know that S is a subset of T, so I want to use that. Namely, the fact that S is a subset of T tells me that X is an element of T. Right? That's what being a subset means. It means that if something is an element of the smaller set, it's also an element of the bigger set. And again, I'm spelling out, I'm combining this piece and this piece to get this conclusion. Just again, so the reader doesn't have to hunt all over to figure out how I'm getting that conclusion. But I know something about T. Namely, I know T is lonely. Namely, since T is lonely, and X is in T, X plus 1's not in T. How do I know that? That is literally the definition of being lonely. But of course, I don't want to know that x plus 1's not in T. I want to know that x plus 1 is not in S. How am I going to get that piece of information? So I'm doing this on a separate sheet of paper because probably on some level you're thinking, okay, S is a subset of T. That means everything in S is in T. X plus 1's not in T. So since everything is in S is in T, x plus 1 can't be in S either. So that must mean this is the case. But you might also be thinking, okay, we've been talking a lot about logic, and I can't quite follow exactly what that argument is in terms of the pieces of everything that we've written down. So I wanted to, as an aside, spell all of this out. Why is it that if I know that S is a subset of T and x plus 1 is not in T, why does that tell me that x plus 1 is not in S? So let's spell this out carefully. Here's how it goes. So what does S as a subset of T mean? It means that if A is an element of S, then A is an element of T. But that's not actually the kind of thing I want. I really want to know something about not being an element of T. And here is where we have to remember our friend the contrapositive. Remember, P implies Q is logically equivalent to not Q implies not P. This is the thing we called the contrapositive. Not the converse, this is the contrapositive. And so that means that S is a subset of T means if A is an element of S, then A is an element of T. But it also means the contrapositive of this. So it also means if A is not an element of T, then A is not an element of S. This statement, which again feels kind of obvious, but if you try and think about it, you sort of turn your brain into knots trying to figure out exactly how to explain it. This is just literally the contrapositive of the definition of being a subset. And so in particular, since S is a subset of T and x plus 1's not an element of T, then x plus 1's not an element of S. A lot of the times when you find yourself in that sort of logic knot trying to write something down, where it's sort of clear, but you can't quite figure out what to write, a lot of times what's really happened is that you've applied the contrapositive in your head without naming it, and it would just be easier if you wrote down the if-then statement and then wrote down the contrapositive. So going back to where we were in our proof, we've thus shown x plus 1's not in S. And again, why is that? That's because x plus 1's not in T and S is a subset of T. Again, you can spell out contrapositive is the magic word, which will help someone figure this out if they're confused. But now we've gotten where we wanted to go. Namely, we've now shown that if we suppose we have an element in S, that x plus 1's not in S. So thus, S is lonely, and we're done. Let's now do another of these. So let's prove or disprove. If S and T are subsets of Z, and S is a subset of T, and S is lonely, then T is lonely. If this looks a lot like the previous one, it's a lot like the previous one, except in the previous one we assumed T was lonely and then showed S had to be lonely. Now we're saying, if S is lonely, does that mean T has to be lonely? So this one's going to work out to be false. And I want to think again, just to be careful and think through all of this carefully, what does it mean to show an if-then statement is false? So let's recall the negation of if P, then Q is P and not Q. So in this case, if I want to disprove this, what does that amount to doing? That amounts to proving that for some S and T, we have all the if stuff. So again, what did I do here? I chunked this into S is a subset of T and S is lonely. That's the if part. T is lonely. That's the then part. And so the negation of this if-then statement is going to amount to finding some S and T that are subsets of Z, where S is a subset of T, and S is lonely, but T is not. Now, you might be wondering where this part went. And this part, and this is sneaky, this part is really a for every statement. This piece at the beginning, this is really a statement about every S and T a subset of Z. So this piece is sort of the context. It's making a statement about every S and T that are subsets of Z. And so then the negation of that for every is a there exists, which is why I say for some S and T, I'm really there just using a synonym of there exists, or there exist, so that we have this. Now, this is all a long-winded way of saying that what we really need is a counterexample. And I want to stress, we need a single counterexample. That is, I need an S, this is a subset of a T, where S is lonely and T is not. And I claim this works. S is definitely a subset of T. S is lonely, T is not. And so at the end of the day, after all of this discussion, when you actually went to write this up in the homework, the entire solution would be this. Part below the line. This statement is false, or you could write disprove or whatever. S is this, T is this, that's a counterexample. And why is it a counterexample? It's a counterexample because it meets these criteria, but not that one. As we talked about in 2.3, quite often we would rather find a counterexample than prove something. It's often easier. It's often shorter to write. It's often easier to find. And so in this case, this for every statement was false. And as soon as a for every statement is false, it means you get to give a single counterexample. I want to stress single counterexample. Do not get fancy and try and give a family of counterexamples or try and explain why the proof doesn't work or anything like that. Give one irrefutable counterexample. And one irrefutable counterexample is all it takes. If you try and go other routes, you can end up really working yourself into trouble. If you want to pause this video for a second and do a little bit of practice, here's a good example. So we're going to suppose now that A and B are both lonely. Which of the following also have to be lonely? A union B, A intersect B, A minus B. What I would like is for you, again, pause the video, write down counterexamples for those of these things that are false, and then write down proofs for those of these that are true. So, first off here, let's write down the one that's not true. A union B does not have to be lonely. Here's an example. Here, A is lonely and B is lonely, but A union B is not. Note, the way I framed this is really just 3 proof or disprove questions. And so we just disproved the claim that A union B had to be lonely by giving a counterexample. The other 2 happen to be true. So let's prove that A intersect B has to be lonely. Okay, so to start, I'm going to suppose that A and B are lonely. Remember, being lonely itself is an if-then statement. So when I want to show that A intersect B is lonely, I need to show that if I have an element X of A intersect B, that X plus 1 is not an element of A intersect B. So really, to start with here, I want to suppose A and B are lonely, and X is an element of A intersect B. Now, immediately I'll note, what does X is in A intersect B mean? That means X is in A, and X is in B. But now, I can apply the fact that A is lonely to the fact that X is in A, to get from the definition of lonely that X plus 1 is in fact not in A. But now, since X plus 1 is not in A, it's not in A intersect B either, because the only things in A intersect B are the things that are in both A and B. But now I've shown that for an arbitrary X in A intersect B, X plus 1 is not in A intersect B, and thus A intersect B is lonely. Now, a careful reading of this proof reveals a little more. Namely, I wrote this down, but I never used it. And I wrote down that B was lonely, but I in fact never used it. So in fact, actually, although this is what I was asked, and I did prove it, it's actually true that something much bolder is true. So in fact, if you just literally read the proof above, and just take out this piece about B being lonely and the suppositions, you get a proof of this claim, which is that if A is a lonely set and B is any set, then A intersect B is lonely. Okay, and so in fact, that's true. It's a much stronger statement. But if you stare even more, you might come to notice that this looks awfully familiar. In fact, why does it look familiar? It looks familiar because, in fact, A intersect B is by definition a subset of A. Right? Because A intersect B is the set of things that are in both A and B, so every one of them is in A. So A intersect B is a subset of A. But what was the first thing we proved about lonely sets? The first thing we proved was that if I have a lonely set and a subset of it, that subset is automatically lonely. So if I take this and I call this the 2020 theorem, then I can actually write down a much cleaner proof of this claim. Namely, all we really have to write is this. Suppose now that A is lonely. You can also suppose that B is lonely if you want, but as we saw above, you don't have to. Then A intersect B is a subset of A, just by the definition of intersection. So by the 2020 theorem, which said that if you have a subset of a lonely set, then it's lonely, A intersect B is lonely, and then we're done. This is really the point of theorems. Theorems are if-then statements, which you can then apply in the middle of other proofs. So in this case, we got to basically take the whole proof of this statement that we wrote down, and we got to avoid repeating all of that proof by just citing this result. The more math you learn, the more theorems you learn, and the more your proofs tend to amount to citing theorems instead of just unwinding definitions. Every class that you take is going to start with unwinding definitions, but then the more you unwind the definitions, the more things you prove about the definitions, then the more properties you learn, which you can then apply as theorems in the future. To wrap this up, let's look at A minus B. I claim A minus B also has to be lonely if A and B are lonely. But why? Well, in fact, it's exactly the same proof here. Namely, I just have to replace these intersections with minuses. Again, by definition, A minus B is a subset of A. It's the set of things that are in A but not in B, so it's things in A in particular. And so by, again, the 2020 theorem, A minus B is also lonely. None of this, by the way, makes this longer proof that if A and B are lonely, then A intersect B is lonely. None of that makes this wrong. This is perfectly correct. It's just longer than necessary, and it doesn't note some of the connections that are there for us to find. Some of you, though, will have come up with a different answer to the question of whether it has to be the case that if I take the intersection of two lonely sets, I get something lonely. Namely, if you thought about it, some of you would have thought of something that looked like this, where both of these things are lonely, but their intersection is the empty set. And so it might have occurred to you to think, okay, well, the empty set probably is not lonely, because it can't be true that something for every element of the empty set, blah, blah, blah. But the empty set is lonely. And this is an annoying technicality that is going to come up a lot, so it's worth thinking about. Namely, what does saying the empty set is lonely really mean? It means I'm saying that for every x in the empty set, x plus 1 is not in the empty set. Now, again, you might not love talking about every element of the empty set because, again, the empty set doesn't have any elements. But it's useful to remember that this for every statement I can rewrite as an if-then statement. And this, the if part, this is always false, right? The empty set has no elements. So the claim x is an element of the empty set, that's always false. And I want you to remember that one thing that's true about implications is an implication is true as long as the hypothesis is false. Whenever the hypothesis is false, the implication's true. In this case, though, you can actually go even further and note that the conclusion, the x plus 1 is not in the empty set, this is in fact always true. And we had also said that for any implication, if the conclusion is true, the implication is true, regardless of the truth of the hypothesis. Again, the only way for an if-then statement to fail is for the hypothesis to be true and the conclusion to be false simultaneously. And actually, in this instance, neither of those can happen. But let me be a little bit more general. Any statement that starts for every x in the empty set and then says anything about x at all, this statement is always going to be true. And it's not going to feel right for a while. It's going to be frustrating, and you're going to think back and forth about, like, wait, which way does this work? And it'll be slightly confusing. But what would it mean if this was false? Well, what does it mean when a for every statement is false? When a for every statement is false, it means there's a counterexample. But a counterexample to a statement about every element of the empty set would of necessity be a statement about an element of the empty set, which, well, there aren't any. So there can't be a counterexample, because, again, there are no elements of the empty set. So, again, conclusion, any statement about every element of the empty set is automatically true. This statement has a companion statement. Namely, the companion statement is to replace the quantifier for every with the quantifier there exists. And so if I write down a statement like there exists x in the empty set such that, and then again, anything in the world you could possibly want, this statement will always be false. And it will always be false because I'm never going to get as far as there existing an element of the empty set. So it just doesn't matter how easy or true this thing is, there's never an element of the empty set that makes something true because there are no elements of the empty set. I'm sure we'll talk about this pair of facts a number of times throughout the course, because these things have a tendency to come up a lot. But try and internalize this now, try and think through these two, and make sure it sort of clicks why exactly it is that these two things work the way they do, and hence why it is that the empty set is lonely, even though the statement about every element of the empty set isn't very profound. Okay, I'm going to wrap talking about direct proof there. On Monday, when we meet to talk about this, I'm going to give you a different definition and a similar list of statements and let you work on them, and then we'll talk together about deciding whether they're true or false. But that's all for now. I'll see you next time.